Right, I guess it's time we started, got this show on the road. Thank you all for contributing to the quiz. I think there was 23 people who've put in submissions. We don't know who you are because you're all under pseudonyms, some of them better than others. But anyway, thank you all for joining in and being part of this event. It's a shame that we haven't got coffee and biscuits to go with it, but we'll just have to make do. I know it says New Year quiz, and it seems a while ago since New Year, but it's still January. Seems longer, I think, during lockdown. Anyway, let's get going. So the first question was about Ceres, the largest known asteroid in the asteroid belt, and its mean distance from the sun in astronomical units, and the answer being 2.8. Now, so here we got plotted out the distances for various the objects in the solar system in astronomical units, and this is a really good way of remembering these things. So if you happen to remember, the asteroid belt is between Mars and Jupiter. Earth is 1 astronomical unit, that's the definition, and the planets all go in quite a easy to remember sequence. Well, the first two are a bit awkward. So Mercury is about 0.4, rounding up, Venus about 0.7, Earth 1, Mars 1.5, Jupiter 5, Saturn 10, Uranus 20, Neptune 30, and if we went on to Pluto, that's 40. So that's the only way I can remember them, is to work in astronomical units. So being between Mars and Jupiter, it's going to be somewhere around the 2 to 3 sort of range. So that's what it turns out to be. And indeed, here we have, James has plotted it on a log plot, and you can see they all sort of line up quite nicely. I think that's something to do with Bode's law, is it? Or is that to do with moons? I've forgotten. Chime in if you want to, James or Richard, with an answer on that. And this is how you all did, pretty much, well, 18 out of 22, is it? Yeah, 22 got that right, so well done, everybody. If we move on to question 2, I'm hoping, oh, there we go. The International Astronomical Union decided in 1922 that they'd fixed the number of constellations because they've moved around over the years. But anyway, they settled on 88, so there are now 88 known constellations, and we had a talk on this a few months back at one of the Plumtree online meetings, saying how they sort of moved around a bit, and some of them were broken up and sort of defined in the 1500s and 1600s, or some of them going back to Greek times. But anyway, that's the number of constellations we've got, and say the International Astronomical Union defined the 88 constellations back in that time, 1922. So how did we all do on that? Quite a few people got this, a few either side. Nobody went for the 209 option, so well done. Another good answer to that one. Question 3, common name for the companion star to Sirius, which is also known as Sirius B. It's a white dwarf. I think it was the first white dwarf ever found. And it's known as the Pup because it's a really tiny star. Very difficult to see because Sirius is so bright, and Sirius B is so tiny. White dwarfs are about the size of the Earth, so next to a huge star, they're very difficult to see anyway. But this is its progress over the years. You can see it sort of goes around Sirius A in a nice ellipse. And where are we at the moment? 2020. So it's about at its best point to be observed in the next few years. Once we get round to 2044 or whatever, it's going to be pretty tricky. But telescopes will be fabulous by then, so that'll be all great. So how did we do with that? Quite a few people had a good go at that. We've got the Pup and Pup. A few things, Dog Star Bro, I'm not sure whether that is. Fido, very good answer. And the Puppy, yes, also very good. So well done everyone for that one. Now this one, this is clearly a James question. what celestial target does this graph represent? It shows the angular size of the object as seen from Earth over the course of the year. So angular size being the size it appears. So most planets get bigger and smaller as they get nearer to the Earth or further away in their orbits. And in this case, we can see it's getting bigger and smaller several times over the year. In fact, 1, 2, 3, and it's starting on a 4th. So that must be some planet that moves quite quickly because it's getting closer and further to the Earth over that time. So the possibilities are, probably Mercury, Venus, the Moon, Mars, Jupiter. Anything else is going to be difficult to see. Anyway, the answer is, as you probably worked out, is Mercury, because actually Mercury is the closest planet to the Earth, oddly, in that it spends more of its time near to the Earth than any other planet. So just because of the speed they move, you see there, we sort of see Mercury come close to the Earth nearly 4 times of the year, whereas Venus is only every so often. In fact, I think the next picture is Venus. That's Mercury. Oh, where did that go? So yes, 12 people for Mercury, 2 people for Jupiter. The sun doesn't really change very much, so we haven't got much change on that. You see here, Venus doesn't sort of only gets very close once during the year because we're sort of chasing it, catching up, trying to catch up with it for quite a lot of the year, and then it goes away. So it's a bit of a tricky one to catch up with. Mars, even worse because that's going even slower. And Jupiter, also not very often that comes very close. And the sun, I didn't know that moved. Well, okay, I've learned something new there. I see James has joined us now. Well done, James, for getting back from jabbing people in the arm or whatever you've been doing.
You did well to cover up the fact I wasn't here. Thank you.
He was just getting coffee or something like that. He was getting cake for everybody. That was fun. So on to question 5, the Hubble classification of galaxies. What group name is given to the galaxies in each of the coloured circles? Don't know how we all did here. So anyway, the answer is the green are ellipticals of various sizes. So the ones on the left are ellipticals that are almost spherical, and the ones on the right of the green circle are very elliptical galaxies. And then we've got the red barred spirals down below and the blue spirals without bars in between, up above rather. And the ones in between are S0 or lenticular galaxies. Guess James was feeling kind to you there not to throw that in. So guess we did pretty well on this. I think more than half the people got that right. Very good. Right, James, this is one of yours. You can do this because I'm not very good at observational astronomy, as you know.
Oh, you are. Right, so this is an image of Orion, and it's what in the sky does the red arrow and the blue arrow, what stars do they point to, and the green arrow, what constellation? I can't click the screen.
Oh, I can click the screen for you.
Thank you. So obviously, if you follow the belt of Orion down, it goes to Sirius, the brightest star in the sky. And if you follow the belt up, it goes to Aldebaran, and it goes on to the Pleiades further up. And the green arrow goes to Gemini. And a lot of people got this right.
Oh, sorry, I jumped.
No, that's fine.
Oh.
So what's happening?
Sorry. There we go. That's the answers. Yeah.
Yeah, lots of people got it right. I was quite generous with the marking, so if like the puppy, I gave it a mark, but not Fido. So a telescope's got a focal length of 3,000 millimeters, an aperture of 300 millimeters, and a focal ratio of f10. What magnification will be achieved if using a 10 millimeter eyepiece? So I've put some extra numbers in here that you don't need to confuse people. So the focal ratio is calculated by focal length divided by aperture, and that gives you that f number. And the magnification is the focal length of the telescope divided by the focal length of the eyepiece. So in this situation, it's 3,000 divided by 10, which gives you 300 times magnification. How did people do? Yes, most people got that. Well done. So the position of an inferior planet when its geocentric longitude is the same as that of the sun, and the sun lies between the planet and the Earth, and it's what term is used to describe the above? And the actual answer is superior conjunction. So if we look at this image here, we can see the Earth at the bottom and the sun in the middle, and then we've got this planet in orbit around the sun, inside the orbit of the Earth, and it's in 4 positions there. When it's the other side of the sun, that's superior conjunction, and when it's the Earth side of the sun, nearest the Earth, that's inferior conjunction. And then when it's left and right, so when it's as viewed from Earth, when it's furthest away from the sun, it's at its greatest elongation. And it's its greatest western elongation when it rises before the sun, as viewed from Earth. So Venus is at a western elongation at the moment because it's a morning object. And then the greatest eastern elongation is when the planet is furthest from the sun, and you can see it in the evening when the sun's set. And then the other one was apogee and perigee. So in this context, number 3 in this diagram is the Earth, and this is the elliptical orbit of the moon around the Earth. And at position 1, the moon is furthest from the Earth, so that's apogee, and the moon appears small. And at position 2, it's closest to the Earth, and we call that perigee, and that's when we have a supermoon, when it appears bigger, and that's the difference in size. The moon appears from Earth at apogee and perigee. And because of our slightly elliptical orbit around the sun, that's why in that plot earlier that Julian showed, the sun appears to be a bit bigger and a bit smaller throughout the year.
Thank you for that.
I can't remember how many peaks are in the sun, just to qualify that, but I think that's pretty...
Yes, I think there's only a couple.
Because in the winter, in the northern hemisphere winter, we're closest to the sun, aren't we? It always seems illogical. And then in the northern hemisphere summer, we're furthest away from the sun.
Yeah.
So yeah, that's what that sun plot was all about. And most people got this superior conjunction. Well done. So there are 4 planetary nebula in the Messier catalogue. What are they? People are really impressed with people getting these right. So it's M27, the Dumbbell Nebula, 57, the Ring Nebula, 76, the Little Dumbbell Nebula, and 97, the Owl Nebula. And they've all got 7s in them, I realised. And these are some pictures I've got of them. So the top left is M27, the Dumbbell Nebula, and someone called this the Apple Core Nebula, so I gave them the point. 57 is the Ring Nebula, 76 is the Little Dumbbell, and 97 is what's 97? I've forgotten already.
Owl Nebula.
No, was it Owl?
Well, that's what it said on the slide.
Fine, Owl. So people were putting Eskimo and other nebulas, but and the Crab Nebula. So the Eskimo Nebula isn't in the catalogue. And Julian, the Crab Nebula?
That is in the net, isn't it?
Yeah.
That's M1.
Yeah, but why is it not a planetary nebula?
Oh, because it's a supernova remnant.
That's right. Just checking our new chairman's on the ball. Right. So
about half people got that right.
Yeah, the graphs for the free text answers aren't very accurate. But yeah, lots of people got things. I was impressed. So what lunar features this? Roy's taken images of this over the years that I've seen in the journal, and it's sinus iridium. Go on, Julian. Iridium.
Iridium. Yeah.
The Bay of Rainbows. I always want to say iridium, but it's not. There's no I. So you can see top left is the Bay of Rainbows, this feature. Top right is the Mare Crisium. Mare Nectaris is there, sort of middle right. And then Rupes Recta isn't a big feature. It's the straight wall, which is a lovely feature. But you need very good seeing and a nice telescope to make it out clearly. And again, lots of people got this right. Well done. So, what body in the solar system has features with the following names? Dorothy, Esmeralda, Helga, Peggy, and Sheila. And it's Venus. And this is an extract from, it could be Wikipedia, I'm ashamed to say. Craters and volcanic calderas called Paterae on Venus are named for notable actual women. Indeed, all features on Venus are named for women, with only 3 exceptions. They are Maxwell Montes, named years ago for early radar pioneer James Maxwell, and Alpha Regio and Beta Regio. And I meant to look up who Regio was, but I never got round to it. So answers on a postcard, who Regio is.
I think Regio is a feature, isn't it? Like a plane or...
But they're saying it's a non... Oh, I see. It's not actually a male name. It's just not a female name.
Yeah.
Right.
I think.
But no, I thought it was good. There was Peggy and Sheila and Helga and...
Yeah. Does sound a bit made up.
Yeah. So this really split the participants. Lots of people going for Pluto. But we got 4 people got Venus.
Right. This is definitely one of yours, James. I've never heard of this.
You never heard of Donati's Comet?
No, afraid not.
Oh, Julian.
Take my badge away.
We did a comet evening, so you should do.
Yeah, you made a comet.
I didn't make that one.
So Donati's Comet is the Great Comet of 1858, and it was the first comet to be photographed. Unfortunately, the photograph's since been lost. So if anyone looks around in their drawers and finds a photograph of a comet, I think John might have it somewhere. John, keep searching for it. So it was 1858, and that's a lovely painting by William Turner. So the first photograph was taken in 1827, so it couldn't have been prior to that. And in 1839, we got this daguerreotype process was introduced. Now, this is a picture of the moon from 1840 by Henry Draper. It's probably one of the most famous early astronomical photographs. Now, the moon was photographed before this, quite soon after the invention of photography, but again, that photograph's been lost. But yeah, 1858 was when the comet was photographed. And we got a good number of people knew that. Well done.
Good. Well done. Yeah.
I wonder how much Googling was going on.
I think some by we'll see towards the end. I think in some of the names. I think this was one of mine. You asked me to throw in some astrophysical questions, so this one's not particularly astrophysical, but I thought it was quite an interesting one. What was the first man-made object to enter interstellar space? So basically to leave the solar system, and it's Voyager 1, although if you'd asked me before, some reason I thought it was Voyager 2, but anyway, it's Voyager 1, and these are the only 4 things that have left the solar system so far, I believe, and oh no, there's Pioneer 11 as well. So this is kind of a picture of where they all are, not to scale, unfortunately, but there is a little table there showing where they are. So Voyager 1 is 152 AU, so that's left the solar system, as have most of the others. New Horizon hasn't yet. It's still sort of ploughing through the Oort cloud, Kuiper belt rather, not the Oort cloud. The Oort cloud's a bit further out. So yeah, those are on their way to distant stars and should be arriving at them within the next 50 to 100,000 years, something like that. And this was pretty well answered. Say I would have got this wrong if I'd just had a go at it, but lots of people got it right. This is another one of mine. So what is the name for a planet that does not orbit a star? So we've found quite a few of these, and it's a rogue planet. And this is actually one of them with the red circle around it. It's been photographed by, I don't know, some big telescope somewhere. But these have been cast out of their solar systems and just wandering around through interstellar space all on their own. And probably happened within our own solar system. Jupiter was quite a bully early on and created quite a bit of havoc and probably got rid of a few planets at that point. So the other answer is a planetar was an early suggestion for what has now been called a brown dwarf, but it doesn't really have any formal name. A dwarf planet is what Pluto and Ceres and all things in the solar system that are big enough to be round but not big enough to be planets in their own right. And a Templar is yeah, a night. I don't think that has anything astronomical to do with it. And surprisingly, most people got this right. Planetar is a good guess, but because that was proposed to be a brown dwarf. This is a very techie one, so well done if you got this one. Cosmic microwave background is the echo of the Big Bang. How hot is it, and what frequency does it appear at? So it was initially very hot and cooled down over the intervening 13.8 billion years, and so now it's very, very cold, 2.27 Kelvin. So that's just just less than 2.5 degrees above absolute zero, and radiates at 2 millimeters, or largely it's quite a big spectrum, but it's sort of around there, as you can see in this plot. So the peak is somewhere around 2 to 1 millimeter, and the temperature is extremely precise. It's one of the best black body curves of radiation that we've got, and a reasonable number of people did that, so very well done for that, because I think I would have struggled with that one. I knew the first number but not the second. Degenerate matter is another astrophysics one, is a special type of matter, and it's not matter that's really let itself go and given up on things, all found at the center of a black hole, because we've no idea what's at the center of a black hole. Similarly for the event horizon of a black hole, there's things going on there, but we don't know what they are. And but it is what makes up white dwarfs. So it's a very, very compressed form of matter, and it's sort of held up by electron degeneracy pressure, if you wish to know. But it's also found in neutron stars, but it's slightly different type of degenerate matter. So well done if you got that one. That's definitely in the realm of astrophysics. I can see Andrew Green suggesting it should be 2.72 Kelvin, so you could be right. So makes up white dwarfs. Quite a lot of people got that. And luckily nobody went for has really let itself go. Next one, stellar classification. So the sun is classified as a G2V star, and what do the G2 and the V represent? And so the first two are the temperature or the color, depending, they're extremely tightly related, the color and the temperature. So those two go together. And the V just means it's on the main sequence. So I made up a few other strange ones. The sun is also a variable star, but the V in G2V doesn't mean that. So this is just a plot of the temperatures. So you can see here the different temperatures down here from O the hottest to M the coldest, and G is towards the bottom of that, between 4,900 and 5,700 Kelvin. and the 2 just is sort of where along that range it is, so G1, G2, G3 up to G9. And then the V is kind of whether it's on the main sequence. So the blue line down the sort of center of the graph is the main sequence. That's where most stars live. And then they move off that towards the end of their life. And as you can see there, they go up. So there's a class 4, class 3, 2, 1, and they're all sorts of giants or stars that are coming to the end of their life. There's a dashed line down at the bottom, sort of all out on its own. That's where the white dwarfs live, just for interest. And yeah, quite a lot of people got this right. Those who went for type and variable star, very good answer, but not actually completely correct, but still a good answer. Popular filter is O3. So what does the O3 stand for? And this is, I always find this one confusing. So not to worry if you found it confusing too. So it's doubly ionized oxygen. And this is because of the way they count ionization, which is a bit silly, like quite a lot of stuff in astronomy. So if it was just O1, that would be neutral oxygen, so no ionization at all. It's got all its electrons still. O2 would be singly ionized, because you're starting at 1, and it's just the way they count. And O3 is doubly ionized oxygen, so it's been hit by enough radiation to remove 2 electrons and is absorbing radiation there. And the square brackets around it actually means it's in the forbidden zone, which used to mean it's impossible to recreate this on Earth, but it is actually now possible to recreate it on Earth. It just has to be a very, very hard vacuum with oxygen in. So you have a vacuum chamber with, you put oxygen in, and then you try and pump all of it out, and then you try and ionize it. And you can get this O3 with the forbidden line. That's probably as much as you want to know about that. Anyway, well done. Doubly ionized oxygen, a lot of people got that. Triply ionized oxygen, I can see where you're going if you went for that. Obscuration class 3, I don't know what that is, I made that up. Ozone is O3, so that's also a good answer. And luckily nobody went for the silly answer. Here's another astrophysics one. So what does this equation represent? V equals square root of 2gm over r. So it's the escape velocity of any object. You have to be going faster than this to escape. So this is how fast you're going, the v, and this is all the stuff that's related to it. So the 2 is just a 2. The g is a gravitational constant, so never changes anywhere. The m is the mass of the object you're trying to escape from, and the r is the distance you are from it. So if you're going faster than that, you will never come back to the object unless you turn around or something like that. If you're going slower than that, then you will gradually be pulled back by the body. So if you're going slower than that on the Earth, you're going to end up hitting the Earth again. If you're going faster than that, neglecting air resistance, then you'll leave the Earth. Just to throw in some other ones, this is a rocket equation that says how rockets work, because rockets are a bit awkward. And how big a telescope to buy, that's a silly question, because it's always bigger than the one you've got. And the resolving power of an optical telescope is this equation down there, which we covered at a previous meeting. Everybody got that perfectly right. I was most surprised at that. I thought, oh, this is going to be a killer question.
It was the only question that everyone got right.
So either everybody knows that or everybody Googled it. We're not here to judge, though. And another astrophysics one, the sun burns hydrogen to helium, and it gives off a lot of heat and light, as we know, but it also gives off a lot of other things, one other thing. And the answer is neutrinos. And you can see this reaction here is what's going on in the sun, and you can see some sort of lowercase v's, which are actually Greek letter news. But every time one of those happens, you get a neutrino. And neutrinos are very ghostly particles. They don't really interact with anything. Once they're created, they come straight out of the sun at the speed of light. So they come whizzing out of the sun completely unaffected by the contents of the sun, zip through the Earth. There's 100 million of them going through your thumbnail every second, something like that. The sun gives off an awful lot of them. It doesn't give off dark energy. Dark energy, we don't even know what it is, but we're fairly sure it's not giving it off. Gravitational waves, it's not really. It's got to be wobbling at quite a high rate to do that, which it's not doing. And dark matter, it would tend to suck in rather than give out. So that's my justification for those answers. And most people got that right. Gravitational waves, it probably does give off minor gravitational waves, but they'd be so tiny, they'd be very difficult to guess, to measure rather. And yeah, I do like the person who went for je ne sais quoi. A type 2 supernova is caused by one of these things, and it's actually the collapse of a big star. So it's the core collapse, and there's two main types of supernova. There's a white dwarf explosion, which is the type 1A, and all the others are core collapse. So certainly all the type 2s are core collapse. Big star collapsing in on itself. And quite a lot of people got that right too. Well done. And another one, must be coming to the end of my questions soon. Comet with a hyperbolic orbit is, well, it's going to leave the solar system. It's going too fast to be contained by the solar system. So there's, if you studied classical Greek and Platonic solids and all that sort of stuff, you might well have come across ellipses and conic sections. So this is what you get if you cut, they originally came from, if you cut a cone, like an ice cream cone, you stand it on its base, so the ice cream is planted in the desk, and you take different slices of it, you get these different things. So if you slice it straight across, you get a circle, because you're looking down on it, you get a circle, because that's what you see. If you slice it at an angle that is less than the angle of the cone, you get an ellipse. So that's what this is. If you slice it precisely along the same parallel to the sort of side of the cone, then you get a parabola, which is this e = 1. And if you go more extreme than that, you get a hyperbola. And these are also the orbits that comets and planets move on. So we don't really get any circular orbits. We get quite a lot of elliptical orbits, including the Earth, the Moon, the suns. Quite a lot of comets are on very extreme elliptical orbits. And if they're elliptical, they're held by the sun, so they're never going to escape. But if they're hyperbolic, like this, and they come in at so fast that they can't be held by the sun's gravity, and they will shoot off. So we've had at least 2 visitors from other solar systems come and visit us. Oumuamua was the first one, and I can't remember the name of the second one. But we also get some of the comets that visit us. They get knocked out of the Oort cloud, come zooming in. But depending on how violently they get knocked out of the Oort cloud, they can come zooming in and then disappear forever. So very well done. All you geometers out there who knew their conic sections, very well done.
Richard's our resident expert on conic sections. He's got one of those, a cone with all the little bits on.
Apollonius cone, it's called.
What's that?
Apollonius cone.
Right. Okay.
It's a way you can potentially divide the cone by sort of slicing it at different angles to make all of those conic sections and see all the different orbit shapes. It's quite impressive.
They are fantastic. I bet you were all sitting in thinking back to your school days, thinking, I'm never going to need this knowledge of conic sections, but if you remembered it, today it came good. So ranking the following in order of size, smallest to biggest: a parsec, a redshift, terameter, a light year, and an astronomical unit. Anyway, the answer is astronomical unit, terameter, light year, parsec, and redshift. And just to put this in perspective, these are sort of solar system scales. So astronomical unit is the distance from the sun to the Earth, about 150 million kilometers. A terameter is 1,000 million kilometers, or 1 billion kilometers. So it's about 6.6 AU. That was the only awkward one, I think. Then the next two are interstellar scale. So a light year is the distance light travels in a year, and we're getting into about the range of distance to stars. A parsec is about the distance to the nearest star. Roughly, it's about 4 light years to the nearest star, but a light year is therefore smaller than a parsec. And the redshift, which we had a bit of a debate about while setting this, is a huge distance. So a redshift value of 1 is about 100 billion light years, 10 billion light years, sorry, I can't read. So it's about halfway across the universe. The awkward thing about redshift is it's not a linear scale. So redshift 2 is about 3/4 and redshift 3 is about 5/8 or something like that. No, more than that. But anyway, it shrinks up. And the cosmic microwave background is about 1,000 redshift. But anyway, it's a huge distance. Redshifts are what we use in galactic astronomy all the time. And quite a lot of people got that right, so well done. The terameter was the only awkward one, and I have to say I hadn't actually heard of that, but I could deduce what it meant.
Julian, when you said we debated this, can I just add, I was nothing, did not contribute to the debate because I didn't understand it, but I got the treasurer of the British Astronomical Association to go through the quiz to make sure it was mostly logical, and he and Julian had a cerebral debate about this, which I kept out of.
Very wise, very wise. Right, where are we up to now? Oh, Kepler's third law. I guess you either know this or you don't. So Kepler had 3 laws that he worked out when he was working out the orbit of Mars and other things like that. So his first law is a planet sweeps out equal areas in equal time. That's his first. His second is all planets orbit in ellipses around the sun with the sun as one focus. And his third law is that the orbital period is related to its orbital distance. I always get this wrong. I think it's the radius, major radius cubed is equal to the time squared, or it could be the other way around. I ought to know that, but I always look it up when I need it. And the fourth one is Newton's third law, just thrown in there. And yeah, people tended to plump for his first law, which is a good place to start. I think we're back to James with this one.
Yes, so the method here is used to detect exoplanets. And the question was, why is the light bit of the light curve on the left and the green circle, why is that concave rather than square, as I've tried to indicate on the right? And the answer to this is because of limb darkening. Julian, you might have to change the slide.
Oh, sorry. Yes.
That's all right. So we've got an image here of the sun in white light, and you can see hopefully that the limb, the border of the sun is more orange than the center, which is yellow white. And on the next slide I've taken some little samples of across the disk of that same sun, and you can hopefully see that the edges are darker because of the limb darkening, and the center is bright. And what answers did we get? The eyes have it. No, that's not right. So we had lots of people saying because of limb darkening, essentially, but there were some wrong answers because talking about distance of planets and things and atmospheres, but they were wrong. But a good number of people did get it right. Really, you should have this one, Julian.
Okay. So have a go. Where does our sun sit in the HR diagram? In which coloured circle? So you can see there it's green. So the HR is the Hertzsprung-Russell diagram, which both Hertzsprung, Henry Russell, I think that's right, got them the right way around, came up with independently. So if you plot the temperature or the colour, which are sort of one and the same, against how intrinsically bright the star is, they found that most of the stars fit on this sort of band here, the main sequence, because that's where most stars live, and they only go off this main sequence when they start to die or something starts to go wrong with them. So the sun is in the middle of this. The luminosity here is usually given in luminosities of the sun, so that's one solar luminosity, and if you happen to know the temperature of the sun, you can work it out, but it usually sits somewhere in the middle. So down here we've got red dwarfs, and up here we've got some of the more giant stars. Up here are the ones that are going off piste into the supergiants, the red circle. So those are ones that are no longer burning hydrogen, or they're starting to burn it in a shell, or burning helium or something else exotic. So they've gone and done their own thing. And down there you have the white dwarfs in black, which are stars that have given up and stopped burning at all. Okay, so there we have a nice picture of it. The sun right in the middle of that main sequence, and the other things floating around there. And people did pretty well on that one. So very good answer to that one. Back to you, James, I think, for globular cluster.
And Richard sent me a message saying we need to hurry up because we're only halfway through.
Oh gosh, okay.
Right, well, hurry up to keep Richard happy. What category of deep sky object does this belong to? And that is obviously a globular cluster. So a cluster of stars, of suns, and they're dotted around the Milky Way. And we can see here's a galaxy cluster. So this is where some galaxies are associated with one another, and this is the Virgo cluster. Open clusters, this is the Pleiades, and this is Gareth's image. And then this is a reflection nebula, so a cloud of dust and gas which is illuminated from a star within, and that's the Witch Head Nebula. You can just make out Witch's head and the nose and the chin and the mouth, and most people did well.
Very good.
So the saying, the red sky at night, shepherd's delight, concludes with the red sky in the morning and shepherd's warning. Some people put sailor's warning, but I accepted that. And I think it generally means red sky at night means the weather's going to be okay, but if there's a red sky in the morning, it's not going to be so good. So, which of these first magnitude stars is currently closest to the North Celestial Pole? I thought of the question and then I had to delve deeply to work out which was the right answer. And it's actually Capella. So if we look at the declination of these various stars, this is how far away they are from the celestial equator. And the North Celestial Pole is at plus 90 degrees. So the closer their declination is to plus 90, the closer they are to the North Celestial Pole. And that is Capella. And lots of people got that right. So Capella, Vega, they're circumpolar stars, so you can see them all year round. Capella's low in the summer and Vega's high in the summer, and then they change positions. So what's the rotation period of the sun at its equator? And the answer to that is 25 days. And we've got a little graphic here. It's because it's not a solid mass, the different latitudes have different rotation periods, and we see that on other non-solid bodies. And the equator's the quickest point of rotation, and near the poles is the slowest. And again, lots of people did well. Well done. The actor and astronomer, amateur astronomer, Will Hay, I mistyped Hay in the quiz, so I'm sorry, I put H-E-Y, discovered a spot on Saturn in 1933. And that's his drawing of the white spot on Saturn. And you might remember him from some old black and white films of, there was always a chubby naughty kid and an old man with a beard, and there he is with his telescope, and that telescope is now looked after in the West Midlands by someone, I can't remember his name, but lots of people did well with this. Well done. So what astronomically related organization is this the icon for? And it was the top left one, and it's the new icon for the Royal Astronomical Society, and the old one is on the top right there. Now I much prefer the old one, and I'm not really sure why they've changed it. There is logic to the icon. Julian, can you remember what the icon actually represents?
Well, it's a ring of telescopes. But I'm not sure what all the bits are.
Right. And then the next slide shows the icons for the others. So BAA, the FAS, IAU, and ESA. And lots of people did well. Good. So what's this device used for in amateur astronomy? And this is an atmospheric dispersion corrector. Damien Peach talked about these when he spoke to us about planetary imaging. And it's got two levers to the left of the middle. And you move those until you get minimal fringing of blue and red light. And it's meant to help. Richard and I have tried with these. And Richard, what do you reckon?
Not much success so far, if I'm honest. I tried with Mars and struggled to improve the image that much, but I think put more works in order.
Yeah. So here are the other ones. A coma corrector corrects for coma aberration in reflecting telescopes. A field flattener does, as it says on the tin, it flattens the field. So for imaging, you don't get sort of a curved image on a flat sensor. A focal reducer is effectively reduces the focal length of the optical train, so that's used mostly for imaging, but you can use them for visual work. And then the illuminated reticle eyepiece is a normal eyepiece, and it's got those crosshairs etched on the inside, and that silver bit at the side shines a bit of light in, and that illuminates those crosshairs, and you can measure things and get positions quite accurately. And again, lots of people did well. So in planetary imaging, what wavelength is referred to as the methane band? And that's that top one, 890 nanometers. The others, 12 nanometers, I just thought of a silly number. And then the other three are the narrow band imaging wavelengths. So 03 is 496 nanometers, 656 is the hydrogen alpha, and 672 is the sulfur 2 narrowband, and then methane's up the far right. And probably just under half of people got that. Damien Peach does some imaging, others do as well, of using methane filters of Jupiter and Saturn mostly. So what is this astronomically linked building? And it's the King's Observatory, or Kew, the observatory at Kew. And the others, the King's Observatory was for who was the king? It was the third, someone the third.
George, I think, wasn't it?
George the third,
George, yeah.
and the transit of Venus of
1761.
Yeah,
Can't remember.
about there. I'm sure someone will type the answer in. Andrew Green, get looking it up and tell us. The others, Woolsthorpe Manor. So this is Newton's home, not so far away from here. Flamsteed House, at Greenwich for the Flamsteed, the first astronomer royal, George Andrew saying. Burlington House, so this is a big complex in Piccadilly in London, and the Royal Astronomical Society and other learned societies are based there.
RAS is just about there.
Yeah. and Herstmonceux Castle in East Sussex. That's where the Greenwich Observatory telescopes moved to in the middle of the last century.
I had breakfast in there 2 years ago.
Right. Good number of people got that right. Well done. So, what does this image of a defocused star tell us? And the answer is it's suffering with poor collimation. So if we go to the next slide, I think, yes. So if you look at a star through the eyepiece of a telescope, this is usually with a Schmidt-Cassegrain or a reflecting telescope, and take the star out of focus, you see these concentric rings. And if the spacing between them is not symmetrical, it suggests the telescope is out of collimation. And collimating it means to try and get it all symmetrical and make it nice, which improves your view. And lots of people got this well. Someone thought the star had orbiting planets, which interesting, but no. So which of these animals do not feature in the Messier catalogue? A starfish, a cat, a dog, a duck, or a butterfly? And the answer is the dog. So we have the starfish cluster, M38. We've got the wild duck cluster, M11. The cat's eye nebula, M94. And the butterfly cluster, M6. But there's nothing with a dog in the Messier catalogue. Well, I thoroughly searched as much as I could, but if someone finds a reference to a dog something, please do let me know. So only 3 people got that, so a minority. But well done, you 3. Go on, Julian, you can have this one if you want. A bit of sun.
All right, a bit of sun. So what are the correct labels? So there we go with a sunspot, and it's umbra and penumbra, A and B, and then also filaments and a plage, which are other features. So I think a filament is that in eruption basically, but coming towards us. I can't remember what a plage is. It's all solar physics. Don't have any much to do with that. But apparently lots of other people do. So well done everybody who got that. 20 points.
We need to get Lucy Green back again.
We need to get Lucy Green. She'll, the TLP, transient lunar phenomenon. I hadn't heard of these until about 10 years ago or something, and they are transient, aren't they?
Yeah. So in the 50s and 60s, there was a big interest in these sort of things, and Alan Heath tells me there was always lots of phoning around late at night. Have a look at Plato. There's a TLP, and these are people thought there was not flashes of light, but areas which became illuminated or looked slightly different. And there were lots of theories about what these were. Were they outgassing, or was it alien activity or volcanic activity or impacts? And they're kind of going out of fashion now, although the lunar section of the BAA still reports TLPs in the monthly production. And that was a distribution of TLPs, and you can see there's they're all over the place, but they do cluster. But lots of people knew about them, and I made up all the others. The thermal latency period. So who's this man? It's Guy Consolmango, and he's the Pope's astronomer. He's not Brother Cadfal or the Bishop of Southwell. We've got Brother Cadfal top left, Bishop of Southwell bottom left, Bishop Grotesque top middle, and Martin Rees, the Royal Astronomer, bottom. And then who's that on the right?
The baby-eating Bishop of Bath and Wells.
That's correct. I only thought of him subsequently, but I thought I can't change the quiz halfway through. People will moan. but lots of people got the Pope's Astronomer. And he's written books and has done a lot of research about astronomy in the Catholic Church and in relation to the Pope in particular.
Turn left at Orion is probably one of the more famous.
Yeah.
Sky and Telescope.
So when was this first published? The answer is 1941. Lots of people got that, which is good. Now, what do you get? Yes. What number do you get if you add up the principal stars in the following asterisms or constellations? The Big Dipper, Cassiopeia, Cephas. And there we are. So you've got 2, 4, 6, 7 from the Big Dipper, 8, 9, 10, 11, 12 if you add in Cassiopeia, 13, 14, 15, 16, 17 if you add in Cepheus as well. So it should be 17. Yes, and that's what I got. Now someone might argue, but we'll have to let them argue.
Judge's decision final.
Fred's put meteorites hitting the moon could cause TLPs as well. Yes.
Yep.
Meteorite impacts. So which of these constellations contain the most Messier objects? Bootes has none, Canis Major has 1, Cygnus has 2, Orion has 3, and Virgo has the most at 11. So that was the answer. And well done, 14 people. Which of these seas are on Mars? So it's Mare. I should have rehearsed this. Go on.
Erythrium.
That sounds good.
I'm going to go with that.
All the others are on the moon. And there's a little picture there of Mare Erythrium in the southern hemisphere. And again, lots of people did well on that. Go on, Julian.
How big is the primary mirror on the Hubble? Well, it's 2.4 meters, which isn't that big these days, but is pretty big for being in space. And we can see there the JWST, which is 6.8, which we're still hoping is going to go up this year. So how did we do with that? Most people got that right. Well, it's been around since 1990, so it's had plenty of time to catch up with that. In terms of apparent magnitude, how many times brighter is a magnitude 2 star than a magnitude 3 star? So it's 2.5 times. This is because of the crazy magnitude system, which is all log based, because we had to try and retrofit it to people who did it without any measuring, at least rigorous stuff. So people knew what magnitude 0 and 1 and 2 stars were for many hundreds of years, and then we had to fit an equation to it. So anyway, you've got a factor of 2.5 in the equation, something we torture our second years with. But quite a lot of people got that right, so well done. Historic telescopes, that's clearly you, James.
So where's this telescope? So this is the 72-inch aperture Leviathan of Parsonstown, the third Earl of Ross, his great telescope in Ireland at Birr Castle. Yeah, I put in Bath for Herschel, Greenwich for Greenwich, Hurstman and Kew just to confuse people. But lots of people got Birr Castle, and there's a big archive of history of astronomy and particularly of Birr Castle at the castle, the current Earl, who I think's RAS or Royal Society or something. He's quite learned. He looks after the archive. So how many degrees of arc do the stars appear to move in 4 hours in the night sky? And the answer is 60. So every hour the stars appear to move about 15 degrees. So I just put in 4 hours just to make you do a bit of maths as well. So 60 degrees. And again, lots of people got that. Who is this loop of hydrogen alpha rich nebulosity named after? And it's in the constellation of Orion, and it's Barnard's Loop. Tycho Brahe, Chandrasekhara, Eddington, Hubble, just again, astrophysics and observation astronomers just to confuse you. And lots of people did this well. Well done.
Final question.
So the Andromeda Galaxy has 2 bright companion galaxies. What number do you get if you add up all 3 of their Messier designations? So we've got M31's the Andromeda Galaxy, M32 is that little blob just above, and M110 is the little blob just below. And if you add all those numbers up, hopefully you get 173. Otherwise, we'll have lots of complaints. And lots of people did well.
Lots of people agreed with you.
So that was good.
Very good. And now, drum roll and the results, I think.
Is it results time?
It's
I can't remember what the
results
next slide is.
Yes. Norway, can we have your results? Of course, we don't know who any of these people are, apart from a couple who put their real names in. But anyway, that's the results.
So yes, we've got lots of names down the Baz there. Baz did well. Everyone's done well.
Yeah, very well on that.
Roy, David Owen, Brendan. I'm disappointed, Brendan, you weren't at the top.
Yeah.
Andrew Green, very well done.
Yeah,
JSP, good. Me and Google. I wonder who that was. And Messier 74, whoever you are. You are the winner, yes. I was reading about Messier 74 to see if I could work out if it was a cryptic clue to who the person was, but I didn't get that. And anyone who submitted after the deadline, unfortunately, your results aren't included. But I had a quick look today and no one got more. So Messier 74 is... As Sam's name isn't there, I wonder if it's Sam. Sam usually wins the quiz.
He usually does, doesn't he?
So the next slide says what Messier 74 got wrong. So they went for cat in the Messier catalogue, and it's a dog. They went for 18 stars in those constellations. And I wonder if they counted Alcor. I was thinking this. Mysore and Alcor, it's a visual double. We may get a complaint. And they went for Mare Australe being on Mars, and it's not. It's actually on the moon. So if anyone's in the YouTube chat and can reveal who Messier 74 is, we will put the prize in the post. No, there is no prize.
Sterilized
prize. Oh, yes. So Andrew Green about Donati's comet put something in the chat, and I've had a quick look, and its orbital period's 1,800 years. And so it'll be back in 3738. So we've got that to look forward to.
We'll be back out of lockdown by then, I think.
Yeah, we might be out of lockdown. No, we've not had any revelations of who Messier 74 is yet. It would be nice to know who you are eventually.
Eventually, you can do it on a postcard if you wish.
Yeah.
Right.
But no, I think everyone did well, and hopefully it was a bit of fun.
We had fun putting it together.
Yeah, definitely.
When I say we, I have to say James did most of the heavy lifting on this, and I just chipped in a bit here and there.
So
we have some pictures, I think, Richard.
Yes, I've got the some pictures of the Great Conjunction to go through. So quite a few members have sent us some pictures through. So I thought it'd be quite nice just to have a look at those to finish tonight. I have to say, personally, from an event that I've ever seen, I think it's one of the best sort of astronomical things I've seen through a telescope. It was really quite a sight at such high magnification to see the two giant planets in one field of view. Really quite an impressive sight that probably very few have ever even seen. So I hope you all got a chance to see it. the big day itself, I think, for most of the UK was clouded out. So
Clouded.
yeah, so 21st. Unfortunately, we didn't see it, but I think given the weather we've had over the last couple of weeks, I think we should have taken the view that we got the day before, when I think most of the photos that members have sent in were taken. So we're really good, clear night on the 20th, sort of, and low on the horizon. It was very clear as well. So it was actually good. I actually watched the two planets set on the 20th on the horizon, saw them right to the last minute. So it really was good weather. So we couldn't have asked more for that, I suppose. But yeah, quick reminder, that's the sort of conjunctions. So they occur every 20 years or so. So I put Jupiter in the center there, and then all the other circles are the position of Saturn, the closest it gets on each of the great conjunctions every 20 years. So there's only one in recent or telescope time, 1623, that was closer. So we're quite fortunate to see that. And then there's this image on the top, sort of right, showing, you probably can't see that actually, my video image is over it. Let me move that out of the way. You can see that the actual how close they are to each other put on the disk of the moon. So you can see just 0.1 of a degree apart at their closest. So let's have a look at some of the images from members on there. So this is one I took, and this was like a mosaic I put together of the actual approach of the conjunction on the nights I saw it, and also the day after, and I managed to get quite a poor view of it. So you could see again Jupiter down the bottom here, centered in the same position each time. And then you can see, so on the 15th, I think was the first one I got. These were taken using the ED80 Skywatch ED80 camera with the Canon 6D. So you can see the approach as it got closer, and that was the 20th when we probably had the best view. And you see some of the moons of Jupiter there as well. I couldn't quite pull out the moon on Saturn. I couldn't quite get that in the exposure. I've seen one or two images that have picked that out nicely, but it was a real challenge, I think, to image the planets, because the sort of the contrast, Saturn being so much dimmer than Jupiter. It was really quite difficult to get the exposure right to see both of them really well and pick out the moons. I've seen some fantastic images online, and Pete Lawrence took, I think, the best that I saw of the two on the 20th, where you could see the red spot on Jupiter really well. It was a fantastic image. Saw it on the 22nd, which I don't think many people saw. So there's a real small gap in the clouds. Literally only saw it for about 10-20 minutes. So I got a few images on the 22nd. That's the image at the bottom right, which why the contrast is a bit different there, because that sky was actually still quite bright at the time compared to those other images. This is the best I managed with on the C11, so the highest magnification. That's taken with the Zero planetary camera. You can just about make out the bands on Jupiter, and probably not on the resolution out to YouTube. You can just about see a couple of the Galilean moons as well. So images from members, thanks so much for sending them through. They're in the journal as well if you want to have a look through, but I've just put them on the slides now. So Andrew Green's here taking through. I think that just shows what a challenge it was to actually image, because it's really low down in the sky. You've got to have a good decent horizon really to see the event over in the western or southwestern sky. So I think Andrew said in his comments on his email with the images how difficult it was to see from his back garden. So he's done really well there just to squeeze it in between the house, the fence and the trees. David Buxton's taken this image of the conjunction. This was taken the 20th as well. Really nice image there in the evening sky. And that's another one from David. I like this one because it really puts the context of the event being sort of near to Christmas. So he took this on Christmas Eve, 24th. I don't think I saw it on the 24th, and that was really good, showing it with the Christmas lights in the background. Shirley showing us what we can do with the iPhone. So she used her iPhone 10 there on her Newtonian, so a bit of eyepiece projection, putting out the two planets there. Again, I think that was taken on the 21st. Mark Fairfax has sent us one here as well. I'm not sure what camera you used, Mark. I don't think I could get that out of the image file. one from Brendan. I think got this one off Twitter. Brendan, we tweeted from the Society account. Really good exposure, showing all the Galilean moons there on that image. Not sure if you can see any of the Saturn moons there. Might just be there if we bring out the exposure a bit more. Roy Gretton, so our journal editor Roy, taking these images from Langer with his Canon camera. Again, nice silhouettes there of the trees behind. So we're taken on the 20th. Image from Marcus here, and I've put these two together that Marcus sent in. So this was on the 19th, this one, and then he's taken another image which I'll just flick to on the 20th. So that's quite nice, just showing the movement between the two over the course of the day. So you see it actually moved quite a bit, not quite line those up perfectly, but you can see the change in separation just in that short time frame. Another one from Marcus, that looks like it's over Nottingham City. I don't know what that cooling tower is in the background. Is that the Ratcliffe-on-Soar power station, or is that the one at the uni? I'm not quite sure where you're looking from to take those images, but it's a nice one. Looking over the lights of Nottingham. And that was just the one I took. I think that was taken with the Canon camera attached to the C11. Really I found it quite difficult because I wasn't on solid ground. I was on the deck of the observatory, which is sort of on a wooden platform. So trying to get any images from the C11 was quite tricky because it was a lot of bouncing around. So sort of try and get that compromise between getting the sort of Saturn light to come out in the image and then having a long exposure, trying to not get any image shake is really quite difficult with that setup. It was much easier using the planetary camera, but that was the Canon 6D on the C11 telescope with a ×2 power mate. Again, a really brilliant sight through the eyepiece, and probably the thing with the event, it was a much better event for the visual observer, I think, than the astrophotographer, unless you're Pete Lawrence, who took a really spectacular image. And I think Damien Peach, did he get the APOD of the day, the astronomical picture of the day for his image? I think that was taken from the Chilescope. I'm not quite sure, but I vaguely remember seeing that one as well. That same image or same setup, just with the exposure altered to try and bring out the Galilean moons. You see a bit of the atmospheric dispersion in that image because it was getting quite low, I think, by that time. Yeah, 619, so it was starting to get quite low. Unfortunately, none of those images showed it as its very closest approach, so that was on the 21st, so that's just what we would have seen. But I was more than satisfied with the view I got on the 20th, I have to say. I think it was a really, really nice event to see, and one we won't see as good again probably in our lifetime. So a successful astronomical event, which is always nice to see, and great to see so many members sending images in. And I think I thought that as an event that it seemed to really attract quite a lot of public attention. A lot of my colleagues at work knew about the event and were asking about it over the sort of week in the approach. So it's quite a nice one to everyone could get involved in, even if you didn't have a telescope. So it was a really good one. Good, that's it on conjunction. Any more from Julian James before we close tonight?
No. I think the next plum tree meeting, Julian, are you and people going to sort that out? We haven't got an exact title yet.
We haven't got an exact title, but we've got some
ideas.
Progress, yes.
Yeah.
We'll do something there and send something out about that shortly. The next what would be Gotham go-to meeting is Jim Al-Khalili, so that should be excellent. Quite famous guy now, often in the media, and has his own radio series. So that should be interesting. I don't know quite what he's going to talk about, the world according to physics, because he's not really an astronomer, but he's he's a lot better physicist than I am, for sure. So I'm sure he'll have some very good insights.
I'm sure he'll keep us entertained, won't he?
I'm sure he will. He knows all about speaking to public.
Cool. Any questions on the live chat before we wrap up? I've not been looking at that.
No, lots of fun about the quiz. That's good. John said it's a spiral in the fishes. Now,
I think that was to do with one of the conjunction photographs.
oh, I thought he'd been drinking something funny, and
He might have been doing that too, but
I don't know what that means. But yes, and great pictures. That's good. No, it's been good fun and ended with some really good pictures.
yeah, thank you all for joining us. That's made a great evening. So,
Excellent, good. We'll see you on the 4th of February,
February.
for Jim Alkalili.
See you all then.
Cool. Good night, all.
Good night.
Bye-bye.